In metallic conductors, the valence electrons are free to move about the metal without leaving the metal. These electrons are referred to as free electrons. The conductor is said to be in electrostatic equilibrium when there is no net motion of the charges in it. Some basic properties of conductors that are in electrostatic equilibrium are: the electric field inside a conductor is zero. The interior of a conductor can have no excess charge in the static situation. At the surface of a charged conductor, electric field is normal to the surface at every point. Magnitude of the electric field strength at the surface of a charged conductor is E equal to sigma by epsilon naught. Electrostatic potential is constant throughout the volume of the conductor and has the same value as inside on its surface. A cavity inside a charged conductor is electrostatically shielded. Now, let us look at each property in detail. One, electric field inside a conductor is zero. Consider a conductor whose free electrons are distributed uniformly throughout. Let us now place this conductor in a uniform external electric field of strength E directed towards the positive x-axis. When the external electric field is applied, the free electrons in the conductor accelerate towards the left. This causes a plane of negative charge to be present on the left surface. This, in turn, causes a plane of positive charge to be present on the right surface. These planes of charge create an internal electric field whose strength is denoted by E dash, opposite to that of the external electric field. Within a short interval of time, the surface charge density of electrons present on the left surface increases, until the strength of the internal electric field becomes equal to that of the externally applied electric field strength. As a result, the net electric field strength inside the conductor becomes zero. It proves that any net charge on the conductor must reside entirely on its surface. 3. At the surface of a charged conductor, in electrostatic equilibrium, the electrostatic field should be normal to the surface at every point. To prove this, for a conductor in electrostatic equilibrium, let us assume that the electric field E due to the charged conductor is not normal to the conductor but as directed. In that case, it will have a component parallel to the surface of the conductor. Then, the free charges on the surface would experience some force and move along the surface. 4. Electric field strength E at the surface of a charged conductor is equal to sigma by epsilon naught into n cap. Let the surface charge density be sigma. We know that the surface charge density is defined as the charge per unit area of the surface. Surface charge density is equal to the ratio of the total charge on the surface to its area. Let us consider a Gaussian surface in the shape of small cylinder, which is part inside the conductor and part outside the conductor, such that its flat faces are parallel to the surface of the conductor. Since the electric field strength at any point just outside the conductor is normal to its surface at that point, we do not have any electric flux through the curved surfaces of the Gaussian surface chosen. We also know that electric field strength E is equal to 0 for any point inside the conductor. And hence, the electric flux through the Gaussian cylindrical part inside the conductor is 0. However, there is electric flux through the flat face of the Gaussian cylinder just outside the conductor, as the electric field strength E is perpendicular to the flat face. According to Gauss' law, the electric flux phi through this area will be equal to integral E dot dA. Here, integral E dot dA is equal to integral E dA cos theta equal to integral E dA, where cos theta is equal to 1 since the angle between the vectors E and dA is 0 in this case. Since E is constant through the flat face of the small Gaussian surface chosen, we have phi equal to E into integral dA, or phi equal to EA, since integral dA will be equal to A. Here, A is the area of the flat face of the cylinder. Let this be equation 1. But according to Gauss' law, we have phi equal to Q in by epsilon naught. Here, Q in is the charge enclosed by the Gaussian surface. Since the surface charge density of the surface of the conductor is sigma, we have Q in is equal to sigma A. Let this be equation 2. Substituting equation 2 in the equation for electric flux phi, we get phi equal to sigma A by epsilon naught. Let this be equation 3. From equations 1 and 3, we have EA equal to sigma A by epsilon naught. Simplifying, we get magnitude of E equal to sigma by epsilon naught. If n cap is the unit vector in the outward direction normal to the surface, then we can write electric field strength in the vector notation as E is equal to sigma by epsilon naught into n cap. Electrostatic potential is constant throughout the volume of the conductor and has the same value as inside on its surface. Inside the conductor, the electric field strength E is equal to 0. We know that the electric field strength E is equal to minus dV by dr. If V is constant everywhere inside the conductor, then dV by dr will be 0, and hence E is equal to 0 inside the conductor. This proves that the electric potential V is constant everywhere inside the volume of the conductor and has the same value as that on the surface. 6. A cavity inside a charged conductor is electrostatically shielded. We know that the electric field strength inside a charged conductor is 0. Hence, irrespective of the charge and the electric field configuration outside the conductor, the electric field in the cavity inside the conductor is 0, and the cavity will remain shielded from the electric field. This is called electrostatic shielding. When a car is caught in a thunderstorm, it is advisable for the driver and passengers to stay inside the car, since the inside of the car will be similar to a cavity in a conductor, and hence it will shield from the high voltage electric field that may get produced by the thunderstorm. We know that conductors are characterized by a large number of free charge carriers which move between the atoms of the conductors and also within the volume of the conductors. Metallic conductors have a large number of free electrons. When a metal conductor is placed in an external uniform electric field of strength, say E, we know that charge distribution takes place in the conductor due to the movement of the free charges, and the electrostatic induction occurs in such a way that in equilibrium, the electric field strength E' inside the conductor due to the induced charges is equal and opposite to the external field of strength E. Hence, the net electric field inside the conductor is zero, and the conductor is said to be in electrostatic equilibrium. Unlike conductors, dielectrics like rubber are those materials in which there are either practically no free charge carriers or free charges. Dielectrics are electrically non-conducting materials. A dielectric material can be made of either polar molecules or non-polar molecules. Polar molecules are those in which there always exists a separation between the average positions of the negative and positive charges in the molecule, irrespective of whether it is in an external electric field or not. Such a molecule is called a permanent dipole and will possess a permanent dipole moment. Water molecule is one such example of a polar molecule. In a water molecule, the center of the negative charge is at the oxygen ion, since it is the negatively charged ion, and the center of the positive charge is at the midpoint of the line joining the two positively charged hydrogen ions. These average positions of the positive and negative charges act as point charges, and hence the polar molecule behaves as a permanent electric dipole. As such, we can say that all polar molecules like water, hydrogen chloride, etc. behave as permanent electric dipoles. Therefore, even in the absence of an external electric field, such molecules possess a permanent electric dipole moment. Non-polar molecules are those which do not